All right. This is what we've been doing up to this point, right? We've been taking two vectors. You see I have two vectors here, and we've been adding them together. And you said, okay, well, graphically, sure, we do it. Well, see, this is what happens when I pin it down. Okay, it's fine. There we go. All right, so we put it there, and then we would make a new vector, a resultant vector that would go like this. Cool. That was easy. Graphically, it's really easy, and it's not much more difficult from a perspective of mathematical perspective either, because we knew that this is a right triangle, right? So we have this angle here, and if this side is 3 and this side is 4, well, then we said, okay, well, to get this side, we just take the square root of 3 squared plus 4 squared, and when you do that, you should get equal to 5. So this side would be equal to 5. That's easy enough. We've been taking at least two vectors, sometimes even more, but we also know that no matter how many vectors I give you, even if I give you 10 or 20 vectors, it's going to be the same. Sorry, that's my mess with the microphone. I have to move a little closer. It's going to give you the same thing. So, or it's going to give you, sorry, even though no matter how many vectors we take, it's going to bring it down to just 2. All vectors, you're just going to get 2 vectors because we're talking about a 2-dimensional space. If this is a 3 dimensions that we were talking about, then there would be 3 vectors because it's a 3-dimensional space. So in this problem here, it was quite simple. That's what we've been doing. Now here's what we're actually going to. Eventually we're going to talk about projectile motion. And so what happens if I throw an object and it's moving in 2 dimensions? Because if I throw, like, imagine I was throwing an object in sort of in that direction. Imagine this represents its velocity, the velocity vector. It's not only up or down, and it's not side to side. It's actually both. So in order to see this, in order to kind of figure out, okay, well, what is this going to be, we have to really look at breaking this vector up, because it's just too difficult to do up and down and side to side at the same time. It's certainly possible. You have to, like, plot these plot trajectories in, like, parabolic space, and you have to use a bunch of parabolic equations, and it's certainly possible, but it just makes it more difficult than it has to be. So instead, what we're going to be doing is taking this motion that is sort of complex in 2 dimensions and turning it into more simplistic motion in in 1 dimension at a time. So we'll have 2 basic components to this. In other words, we're going to take a vector and break it up. So it's the opposite of what we've been doing, right? Let me go back. Before, we took 2 vectors and added them together to get a resultant. But now we're actually going to take a resultant, or a more complex vector, and break it up into 2 pieces. Again, graphically, it's pretty simple to see, right? And by the way, whenever I give you these velocities, I'm actually going to give you another piece of information, and that's going to be an angle. So we're going to start measuring angles. Now, angles are typically measured from the positive x-axis. So this would be, you know, looks like a little less than 45 degrees. Let's say it's like 30. Let's say it's 35 degrees. And let me go ahead and give you a vector, the actual magnitude of the vector. Let's say it's going at 8 meters per second. All right. Now, I need my calculator, so I'm going to pause the video. Now that I have my calculator, I'm ready. Graphically, it's going to be pretty simple to see what we're doing, right? I mean, you could imagine there's going to be some vector along this direction that goes like that. And there's going to be another vector that goes up. Might look like this. It's not perfect, but that's the general idea. We know there's going to be one vector that goes north and one vector that goes east for this vector here. But we want to know, what are the actual magnitudes of these 2 sides? What are the magnitudes of this side and that side of what we're going to call the vertical component and the horizontal component? Now, in order to figure this out, we're relying on the fact that this is actually a right triangle. Very specifically, it's a right triangle. Because it's a right triangle, we have these ratios that are true. And you might have seen them in class before. They're called sine, cosine, and tangent, and you can see them here. Now, if you're unfamiliar with sine, cosine, or tangent, we probably want to go ahead and write this down. It's okay if you start with if you know nothing about sine, cosine, tangent, it'll be okay. there's a whole lesson in itself about the unit circle. I don't think I'm going to go into that in this video. Maybe I'll do a separate video on it, but in essence, they represent ratios of sides of a right triangle, specifically a right triangle. So we have here this mnemonic device called SOHCAHTOA, and they tell us how to calculate it. So SO represents this equation, sine theta equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. That's CA. And TOA is tangent equals opposite over adjacent. So if you're not familiar with these and you don't have them memorized, I would go ahead and write this down in the notes somewhere, in your notes. Okay, now let's apply this SOHCAHTOA stuff. Let's see what we mean here. And what I mean is this. Let's go back to that previous example. Alright, let's label these sides. I'll label them in black. And we're going to label them no we're not. We're going to label them opposite. We're going to label them adjacent. And we're going to label them hypotenuse. So the question is, which side goes with which? Well, this is the longest side. It's also opposite the right angle. That's the hypotenuse. Okay, that one's easy enough. This is the easiest one to find. But the problem with adjacent and opposite is that they are actually relative terms. It depends on which angle we're looking from. And we're always going to consider it from the angle that you're given. If I give you this 35-degree angle, then opposite is going to be the side that is opposite that angle. So imagine this is like a room or something, and you're starting in this corner. You're going to walk to the opposite wall. Well, you keep walking until you smack into this blue vector here, this blue wall. That is the opposite side. And finally, we have adjacent is obviously the one left over, but also adjacent means touching or next to, and this is the one that's touching or next to our angle that isn't the hypotenuse, and that's how we know that these are the three sides. So we have our hypotenuse, opposite, and adjacent side. Now, I could write out SOHCAHTOA for each one of these. Let's start with sine. Now, I'm not going to write the whole thing opposite over hypotenuse because you should have it on the notes, and I don't want to run out of space. But we have SOHCAHTOA means sine of theta, which theta represents, maybe I need to go back for a second. I assume you know this, but this symbol here is called theta. It is the Greek letter it's just a Greek letter theta. And in Greek, it represents the th sound. So in English, we have sort of a T and H that come together to make, I think it's called a diphthong, that makes the th sound. We have two letters that represent that single sound. Well, in Greek, they just have one letter that makes that sound. So if you're going to write the in Greek, it would be like theta. But Greek, it's, anyways, English words and Greek letters don't really make a lot of sense. But theta is what that is. So back here, sine of theta. Now, we actually know theta, right? It's 35 degrees. Though, that makes me another point right here. Whenever we do sine and cosine, it is incredibly important that you make sure your calculator is in the degree mode. So all you got to do on your calculator, hit the mode button. It should be up near the top left. And make sure that DEG is highlighted for degree. You will need that. If you use radians, which is another type, you will get the wrong answers because we are going to talk in degrees, not radians. But they're just different ways of measuring angles. All right, so we have sine of theta equals opposite over hypotenuse. Well, we do not know the opposite side. We do, however, know the hypotenuse is 8. So since I don't know the opposite side, I'm just going to put in y for now. Over my hypotenuse is 8. Y over 8. Well, this is an equation, and we can solve for y from this equation, right? If I want to get y by itself, I have to get rid of the 8 in the bottom. In other words, I have to multiply both sides by 8 times 8 and times 8. Now make sure that it's you're multiplying 8 by the sine of 35. You cannot do 35 times 8 and then take sine. That will not work. Sine is a function. It is something. All right, so we have 8. Multiply both sides by 8. That means that this cancel, and I just have y left. Y is going to be equal to 8 times the sine of 35. Now, this is, again, sort of represents a ratio, but your calculator can actually calculate this. It can look up what sine of 35 is. It is some set value. And it comes from the unit circle. But if you have sine of 35, all you're going to do is you're going to hit, 8 times the sine of 35 in the calculator, and it gives me about 4.588. I'm going to call it 4.6. So y is going to be equal to 4.6 meters per second. Well, we now know this side of the triangle, 4.6 meters per second. Now, an astute student would be able to say, hey, I can figure out this other side using Pythagorean theorem, and you're absolutely right. Or you can figure out that other side using the one of the other trigonometric functions, which is sine. Sine is cosine. You can use cosine. So let's try cosine real quick. I'm going to write out the entire what I call the cosine statement. The cosine of theta is equal to, whoops, I started writing it, so I'll just finish it. Adjacent over hypotenuse. Okay, but this is going to turn into, for us, for this scenario, theta is 35. So we have the cosine of 35 degrees equals adjacent, which I don't know again. This time I'm going to use the symbol x only because it's sort of along the x-axis. X over the hypotenuse, which is 8 still. Okay, to get x by itself, we do something similar. We're going to multiply both sides by 8. And so you get x is going to be equal to 8 times the cosine of 35. And I get about 6.55. I'm going to call it 6.6. Okay, we just figured out this side is 6.6. And you could check it. You could check and see if this is right. You can do 6.6 squared plus 4.6 squared and then take the square. You should get 8. Now, it won't be exactly 8 because we're rounding some, but it will be close. All right, so these are the three sides. And what we have really done is, again, we have discovered these two components. These two components of our hypotenuse, or in other words, this is our velocity. These are the two components of velocity. Y is going to be the vertical component, 4.6 meters per second. X is going to be the horizontal component, 6.6 meters per second. Sorry guys, I'm kind of flipping through. I thought I had, okay, a lot of stuff. Oh, here. Okay. In other words, you can use this to find the vertical component, this equation. And all I did was I took that equation for the y in that case, and I just plugged in, instead of v, because I put our hypotenuse is the original velocity vector, so it's going to be v times the sine of theta. And over here, instead of plugging in x, I put in vx, and this is going to be called the horizontal component of velocity. And it's, again, the hypotenuse, which is the velocity, times the cosine of the angle. And so these two equations here can help you out a lot with the figuring out the two sides. In other words, figuring out the components of that vector. All right, so you see here, for example, it says an object is thrown up with an initial velocity of 20 meters per second, angle of 70 degrees. Find the horizontal and vertical components of this vector. Let's find the vertical component first, Vy. From the previous equation, we have Vy is going to be V times the sine of theta. So our velocity was 20 meters per second times the sine of theta is 70 degrees. So I just punch in my calculator, 20 times the sine of 70. Now, if you're getting anything other than, I got 18.79, I'll call it 18.8 meters per second. If you're getting anything other than what I am, like a really weird or a negative number, that probably means that you're in the wrong mode. You need to be in degree mode, so double check that, please. Degree mode, not radians. All right, second part. That's our horizontal. This is our vertical y, so understand when I say vertical, it means up and down. Just so everybody understands, up and down is vertical. Side to side is horizontal. The horizon is where the sun sets is the horizon, and so I'm using y for vertical component because the y-axis goes up and down. I'm using x for the horizontal component because x-axis goes side to side. I'm about to run out of time, so I got to go fast. Vx is going to be v times the cosine of theta. The only thing that really changes is we're using cosine instead of sine. So 20 times the cosine of 70 is 6.84. We'll call it 6.8 meters per second. Simple enough. So you can use these two equations to break up vectors. Now we're going to see how we use these broken up components later, but for now I just want you to be able to break up vectors. After watching this video, you should be able to take our first assessment on vectors.